cloud. All right, so for those of you who are looking at the recording, I'm sorry I missed the first two pieces. We can pick on that on later. So on the third task set, now that they have looked at data and realized that, in fact, things are getting warmer, and they've looked at the simulation and kind of got the sense of which gases are causing the temperature to go up, we now want them to understand, how does this impact matter and our experience of matter? So we start with looking at density and states of matter so we can trigger back to some knowledge that they already have and kind of go deeper on it if they didn't quite fully get it in middle school, because there are some gaps there for some folks. And then we go into how it relates to kinetic molecular theory. So that so KMT, or the idea that when things move faster, when they heat up and they have more energy, they move faster, they spread further apart. And then we apply that to something that's been in the news a lot about sea level rise. And so how the sea levels are rising and why they're rising, and it's due to a lot of that thermal expansion from that increased energy. After they've sort of got that sense of what's causing that to happen, then we also look at other aspects of the atmosphere that are impacted by the increased energy and the speed of those particles. And so we look at what makes it rainy and cold versus warm and dry. And this is looking at the relationship between that temperature and how does it affect pressure, and how those relationships allow us to look at weather predictions and how that might impact how certain weather systems have more energy and cause more problems for us. After they got that idea, we're kind of narrowing it back down from just all of the things that we've seen for the world around weather and climate and the sea level rise, and bringing it back down to a specific location, to a specific person. This is sort of the idea of a place-based project, but not necessarily the place where you live. So we're taking some sort of piece of the world that they're either interested in visiting, or they have family, or their ancestors came from, any of those pieces, and they're making an infographic explaining how climate is affecting that area that they're interested in. It could even just be someplace that they want to visit, but they should look into how do all of these changes impact that part of the world specifically, and all of the systems associated with it. The learning objectives for the whole unit is to use models to illustrate temperature and pressure and volume and how they affect the motion of particles and how that relates back to the climate change, because we're looking at it in the water, we're looking at it in the air, in other ways. And we're using this sort of anchoring phenomenon of the atmosphere and the hydrosphere, so like the sea and the fresh water, and how they influence each other and impact the biosphere, so all the living creatures, both locally and globally. And the essential question we have folks looking at is, how are these recent interactions between the hydrosphere and the atmosphere impacting our personal lives? And that gets us back to that infographic at the end, where they're looking at how it impacts groups of people.
So we wanted to talk a little bit about why we choose to start with kinetic molecular theory. For those of you that have either attended the physics PD or have taught the patterns physics class, you're very well aware that at the end of the year in physics, they are really focused on energy transformations. They are looking at types of energy. They are looking at creating a 50-year energy plan, where they're trying to project what types of energy we should be striving to convert towards in order to avoid burning fossil fuels. So we really want to kind of catapult off of that and start with energy in chemistry. So it links very clearly back to physics. Also, we have some very basic patterns, like our first pattern that we're going to do in this particular unit is proportional. And so again, that's helping students to go back and revisit those patterns that they've learned in physics the previous year. And proportional is, one of the most accessible patterns for students to understand and be able to articulate. So it creates a nice smooth on-ramp for students, kind of refreshing their skills. We want them to kind of bring back those Desmos skills also that have probably gotten a little rusty over the summer. And then some things that we're focusing on in the unit is that not only are we having energy and matter, as the focus of our unit, but then we're also really looking at modeling as well. And I think modeling is really a skill that's going to be important for students throughout chemistry, because unlike physics, most of the things that they are going to be attempting to study in chemistry, they can't make direct observations with. So learning to draw a model of something helps them to better understand all the components of the model, how they work together, how they influence one another. And so setting the stage for that at the beginning is a great skill builder for students. So we start with our Unit 1 opener. We did this in my class last week. So at the beginning of each unit, we start by having students either look at videos, read articles, analyze data sets, and those are carefully chosen to hopefully be data sets that are related to what they should learn in the unit. And so this is to engage them, to cause them to care about the topics that we're hopefully covering and learning about in this particular unit, connect to their real lives, right? Provide relevance, and then also get them to generate questions. And the idea behind generating those questions is to create a driving question board that ultimately, they think is driving the unit, and that each time we go through a task set or go through a lesson, we're able to pull more of those questions off of the driving question board and be able to answer some of those questions. Now, not all of the questions that they're going to come up with are you going to answer through this short series of lessons, but that's also why I like the project at the end, that it's very much more open-ended. They can choose the place that they want to focus on. They can choose the climate problem that they want to focus on. So that's a great way to address those other questions maybe that students have come up with that we haven't gotten to address, throughout the course of the main task set units. So the essential question that we're thinking about in that Unit 1 opener is, how have our local climate, weather, and patterns changed over time? So I did put a link here. We're not going to do the unit opener today, but I did put a link here to the slide deck for the unit opener. So if you click on that, it goes to our new unit opener. So this is a new unit opener. We revised it this year. We really tried this year to make it much more tied to how the different spheres are influencing one another. And so we have like temperature data, we have wildfire data, we have some glaciers, and certainly we don't think that in your classroom you should look at all of these slides. I can tell you that it took me almost 90 minutes to do the unit opener, and I certainly didn't use all of these data sets, but we put in some different data sets so that depending on where you are, that hopefully you can select ones that are going to be most relevant to your students. So that's a little bit about what the unit opener. Also, we try to vary what they're looking at as well, like satellite images. We have some glaciers here, bar graphs, line graphs, that kind of thing. So that, again, students are able to make observations and then come up with questions from those. So that's a little bit about what the unit opener looks like. There's also a note-taking sheet for students that's linked here as well that is also new. And so this kind of would have the main data sets that you would be looking at with your students. So again, depending on what you're selecting, depending on your area, you might swap some of these out depending on what data sets you really want to focus on. But here we have temperature, then we have wildfires, we have glaciers, sea level rise, and then we also have available water, right? So that's the one that is in the bottom. And so again, just a place for students to write down something that they notice and then something that they wonder. What I did this year that I felt really worked well with students is I actually started with the pictures of the glaciers, and I modeled for students what types of observations that we were looking for in these data sets or these pictures. And then I modeled for them how we would turn those into questions. Because what I have found in the unit opener in the past is that students are great at coming up with questions, but they are not necessarily always testable questions where there's an independent and a dependent variable. And so we generated or brainstormed a bunch of questions, and then we were able to kind of narrow that list down on which of these questions are really good questions, right? Really testable questions, things that we could use the practices to engage in and study over the course of our unit. And I definitely felt like that time of modeling to them what was expected definitely yielded better questions. So I took some pictures of my students' questions. I'm going to share those with you in just a second. But right here, this kind of is just the flow of creating a driving question board, right? So students have questions. Those questions are based on phenomenon, things that they see around them in the world happening. We're going to use the cross-cutting concepts of matter and energy and the scientific and engineering principles of modeling to engage in investigating those, also inquiry. And then eventually we want them to end up on the other side, being able to have a good, solid understanding about the disciplinary core ideas. And so this lines up very well with like creating interest, that interest turning into motivation, leading to engagement, and eventually resulting in achievement. So we've kind of gone through the flow of what you do for creating the driving question board. So I'm going to just skip through this slide and I'm going to jump to this next slide. So these are all pictures of sticky notes that are hanging in my classroom right now. And so these are all questions that my students came up with. And so what I did is that, yeah, in the classroom, we ended up organizing them by the sphere that was going to be affected. But really what I did for all of you is a kind of arrange them by what task set you would answer these questions in, to kind of show again that you really want to be returning to this driving question board as you move through the unit and saying, oh, we can answer this question or this question now. So one great question that relates to the greenhouse gas task set 2 that one of my students wrote: how does the presence of water vapor in the air affect the average temperature? So one thing that they're going to look at in the greenhouse gas lesson that we're going to walk through later is, what effect does water vapor have in the atmosphere? Does it have a warming effect? Does it have a cooling effect? Does it have no effect? So that is a question that we will be able to answer at the end of that lesson. And then if we go to task set 3, that's our sea level rise. Definitely had some great questions there as well. So we have this one: how does the height of the waves affect the erosion of the terrain? Because we looked at some pictures of erosion on our coast. And then, is climate change worsening faster in different regions than others? So one thing in that lesson that we look at is sea level rise on both of our coasts and how they are not happening at the same rate on both sides of our coast, and trying to understand why that is. Here we have, I wonder how the movement of particles contributes to climate change in the atmosphere. And so that lesson is really about how the air temperature or the air particles are transferring their energy to the water particles. So again, a lot of modeling going on in this particular lesson about what's happening with the spacing of the particles and their amount of kinetic energy. How does temperature affect sea level change? So that's kind of tied in there. And then how does the strength of the tide affect the rate of erosion for the geosphere? So all of those are kind of falling under the umbrella of task set 3. And then our students are very concerned about wildfires, obviously, because it seems like every fall when we start school, we are on fire somewhere in our state. So several questions that were generated about our fire season. So how does less and more rain affect the biosphere? How does the increase of temperature change cause or change how many wildfires are forming? How does the air temperature affect how many tornadoes are formed? So that's a little bit more, storm related. So we couldn't find any examples per se of just lightning strikes or thunderstorms, but we did find some tornado data to look at, and that's at least an indicator of those severe thunderstorms that are happening. So lots of great questions here. I would say by far, these are the best questions that I have ever gotten out of a driving question board. So I really feel great about the changes that we've made to the Unit 1 opener, and feel like the data sets and the images are right in line with the types of questions that we want students asking. So as we come to the Unit 1, kind of the end of the Unit 1 opener, our objectives is that we want to practice this skill of, creating questions, or this scientific and engineering practice. I have always noticed in my students' conclusions, when they get to the end and they are supposed to write like a new research question that is supposed to start the next cycle, they really struggle with that. So I thought this was a great opportunity to not only look at how our climate and weather patterns have changed in Oregon, but practice that skill of really writing a testable research question, which is something that I have noticed over time that my students really struggle with. So that is, a big objective of the Unit 1 opener, is to practice that skill of asking questions. And the number one thing that students always tell me when I ask them what has changed in their lifetime is they know it's becoming warmer, right? They don't really even need to look at the data sets for them to know that, but it is confirming to them when they do look at the data sets and see that the average temperature in August has gone up about 6 degrees over, several decades, and that also our number of 90-degree days is increasing over time as well. So by the time we get to the end of this Unit 1 opener, I feel like it very much sets us up for going into task set 2, which is our greenhouse gas concentrations and how greenhouse gases work, so that we're able to, understand why the global temperature is going up. So I just want to pause there for a second because that was a lot on the Unit 1 opener. Just want to see if there's any questions on that before we move on to the next task set.
This probably is on the outline, but our teams are we're wondering about like how much time. You said it could take 90 minutes, but like about how much time would you say you would spend on this?
I did take the whole block to basically work on this. So I think I introduced the idea of the project at the very end in the last like 10 or 15 minutes, kind of started to plant the seed about the fact that they were going to be doing a project on a location of their choice and to start thinking about what they wanted that location to be, and that location had to be a place that was negatively impacted by climate change. But it did take quite a bit of time. So again, if you don't want to take that amount of time, I would definitely like shorten the amount of, data sets that they're looking at. Maybe you'll just look at sea level rise and you'll look at temperature and, maybe the wildfire, maybe just look at those 3, right? Maybe not look at the satellite images and some of the other ones. We tried to include all the indicators of climate, but again, there's like 5 or 6 indicators of climate. So you can definitely shorten that up if you need to. Other questions? Okay, well, we're going to move along, but if there's more questions, please just put them in the chat. Matt is monitoring the chat, and so definitely we'll get back to you. Okay, so that means that we're going to move now. So we've just finished Unit 1, so we know the temperature is rising, and so of course we want to know why is the global temperature going up, what's causing that, and so we have to engage in looking at what gases in the atmosphere are greenhouse gases, right? So what's causing the atmosphere to trap heat and warm. And so our phenomenon that we're working with in this lesson is that global temperatures have changed along with the composition of the gases in the atmosphere. So we're trying to figure out the relationship of what's going on that. As the gases in the atmosphere change, how is that influencing global temperature? The practice that we're focusing on here is mathematics and computational thinking. Our cross-cutting concept is energy and matter. And then we're focusing on weather and climate as our disciplinary core idea. All right, so this is kind of the summary page of what we're doing in this particular lesson, but we thought since we have new FETs for this particular lesson and we've done, some heavy revision to this lesson, and also it's not one that we actually do in the summer class, that we would take time to actually go through parts of the greenhouse gases together. So I'm gonna pause on this slideshow. I'm gonna escape out of this now. And if you would please open the slides to the greenhouse gas lesson, the link is at the top right there. And then there is also a link to the student template that's going to have it's going to show you a preview. If you click on that link, it's going to show you a preview. And then if you click use template, it'll make your own copy and it should look like this. Oops. And then the last one is that I made a spreadsheet just specific for this webinar. So it is not the one that is actually linked in the student sheet. So if you will click on the spreadsheet there, that will open you up to kind of this landing page. And so what we do at our school is that we have all the teachers and all the class periods kind of spread along the bottom. And so then students click on their teacher and their class period. So I just called ours webinar and our date there. So when you come into the cover sheet, if you'll just navigate to that secondary tab, that would be great.
And I'm just going to drop all those links into the chat just in case you're having any trouble with opening up the slide deck.
Okay, for our first part of this lesson, we are also going to need the molecules and light FET simulation open. So the slide or the link to that is on slide 2. So when you click on that, it should open up a page that looks like this. And then we are going to press play. Okay, and so we can see that there's lots of different gases that are here on the right-hand side. These are all gases that appear in the atmosphere. Some are more prevalent than others, right? Nitrogen makes up the largest composition of the atmosphere, followed by oxygen. And then we have our other gases in small quantities, right? So the idea here is that we're going to test 5 different gases in the atmosphere. And so the gases that we are going to test are methane, carbon dioxide, water, and nitrogen, and oxygen. I think we're going to have you guys do kind of groups of 5. If you have a group of 4 instead of 5, we're just going to have you test the first 4 gases. We won't have you test oxygen. And so what we want to do is collect some data about how well these molecules absorb infrared light. So we can see at the bottom here that we have infrared light that's selected. And then the other thing that we will want to change in the simulation is we will want to click on the slow. Because in order for us to collect our data, what we're going to do from the right-hand side is we will select what gas we're going to do. So we're going to wait till we get into our breakout rooms and figure out who's going to do what gas. But we'll select our gas from the right-hand side. So as an example, I'm just going to use ozone, because we're not going to test that one for data collection. And then once we're ready to see and collect data on how well ozone absorbs infrared heat or light, we're going to press on the green button. As soon as we do that, the red photons are going to start flying out of the photon gun here and towards the molecule. If the photon is absorbed, it's going to cause the molecule to wiggle and change shape, and then the infrared photon is going to go off in a different direction. If it is not absorbed by the molecule, it's just going to go straight through the molecule onto the other side. So what I'm going to do is I'm going to keep a tally out of 10 photons of how many are absorbed versus how many go through. So that was a yes, no, yes, no, no, no again, no again, yes, no, no. Okay, so that was 10. So it was super quick. But out of my 10, I had 7 that went straight through the molecule, so they were not absorbed. And then I had 3 that were absorbed and then got sent off in a different direction, right? So ozone does a fair job absorbing infrared radiation. And so I would find my group number, right, which is going to be determined by your breakout room. And then I would go over, let's just say this was ozone. If I'm in group 5, then I am only going to record how many were absorbed by that molecule. And then I'm just going to put in my whole number, and then it's going to make a graph on the right-hand side. All right, so Andrea is going to get our breakout rooms ready, and then we are going to send you guys. Oh, go ahead.
Yeah, so I've got those breakout rooms ready. It looks like we're probably going to have 2 groups that are probably going to be 4. So if you're a 4 group, make sure, like Jomae said, to only do 4 of them, and just leave off either nitrogen or oxygen so that we have one of those. Okay. Yeah, anything else you want to tell them before I open?
Just when you go into your groups, you're probably going to be with people that you don't know. So introduce yourself first, and then decide which gas that you're going to test. And then everybody can collect their data and we'll come back together.
You should have been invited to join your rooms. And we'll be popping in and out of those rooms to see if you need help or how things are going, and listen to the cool conversations.
I guess I need to stop my share probably here for a second. Let's see.
Yeah, Kathleen, do you need any help getting into your breakout room? Catherine, do you need any help getting into your breakout room?
Oh, and we've got one breakout room that got the AI note taker.
Yeah, I don't know. Usually, yeah, maybe it's actually a person there. I don't know.
Okay, Matt is in room 3. So how about if I kind of check in on groups 5 and 4?
All right, and I'll check in on 1 and 2.
Okay, sounds great. Okay, everybody, welcome back from the breakout rooms. It looks like we've got some data here. So again, each student is only taking a small amount of data, but when you do it with a whole class, you end up with about 100 samples for each gas, which is great. Again, we're not looking for the data from this FET to really be completely consistent with global warming potentials. What we're looking for is just for there to be a clear indicator to students which of these gases that exist in the atmosphere are greenhouse gases and they trap heat versus not. And so what we would do at this point is that we would copy our graph into our document. So we can do that by clicking on the 3 dots at the top and copy the chart. And then we're going to come back over to our document over here and paste it in. And I tell students you always want to link to the spreadsheet in case people are still making edits. That way you can do an update to your spreadsheet if the bars shift around on your graph a little bit. We're going to do a little resizing. So at this point, what we want students to do is we want them to rank them. And I can tell you that in my classes, some classes came out with similar rankings and some with different rankings, and that's okay. Again, the big picture is just really what gases are greenhouse gases versus what gases are not greenhouse gases. So we have them rank the gases from the most powerful to the least powerful greenhouse gas. And so that's going to mean that they're going to rank them from most heat absorbing, right, to least heat absorbing, which one has the biggest bar down to no bar. And then we introduce the table here that does have the global warming potentials on it. So I'm going to switch back over to the slides for just a second here. Scroll down in the slides and just make this a little bit bigger. So this table actually has quite a bit of different information in it. But again, we really want to draw students' attention to the bottom part, which is the global warming potential. The global warming potential is how much energy a ton of the gas can absorb, but it's compared to 1 ton of carbon dioxide. So we can see that carbon dioxide's global warming potential is 1. And so every other molecules would be based off of that warming potential. So here, what we're asking students to do is either look at their data and look at this global warming potentials and come up with either a similarity or a difference. So in some of my classes, methane was the highest ranked. And so they certainly saw that it seemed to follow this order of the global warming potential. So that was certainly a similarity. But a difference even is that even in the classes that had methane with the highest warming ability in their data set, it usually was only slightly higher than carbon dioxide. Whereas when we look at the actual global warming potential, it's has 20 times the capacity to trap heat into the atmosphere, right? So that's an example of a difference. Another difference that came out in our classes is that if we look at the global warming potential for water, water is listed as Na. So water does do a very good job of trapping heat in. And we know this because water stays pretty cool even when it's hot outside. So it has a very high ability to absorb energy without changing its temperature. But the problem with assigning a global warming potential to water is that the amount of water vapor in the air varies from place to place. And so we can see that here with the atmospheric concentration, that the atmospheric concentration can range anywhere from basically 0 all the way up to 4%. And so I tell my students, think about maybe if you visited the desert before you've gone to, Nevada or Arizona, it's very dry there, not very much moisture in the air. And so, as soon as the sun goes down, it gets pretty cold. As soon as the sun is up, it's pretty warm, right? There's pretty big shifts in temperature. Whereas if we go down to the southern or the southeast where it's very humid, there's a lot of water vapor in the air, we don't see as much difference in the temperatures between night and day. Or same thing if we go to kind of the Midwest around the Great Lakes, again, because there is a lot of water vapor that is in the air there. So we can't really assign one global warming potential to water because the concentration of water varies from place to place. And so this makes it very difficult because the more water vapor that is in the air, the more energy it's going to be able to trap. So again, that's a difference that they usually notice, is that water is not assigned as a global warming potential, but that it is identified as a greenhouse gas. And that is a similarity. Okay, so now we're done with the spreadsheet, so we can close that spreadsheet. And we're done with the molecules and light simulation. And now we are going to launch the greenhouse effect simulation. So click on that link from your document there, and that should pop open our other FET that we're using here. And again, we want to press play. And at first, we want to go into the Waves tab. So now in this particular window, what we're trying to do is just qualitatively kind of find out, now we know what gases in the atmosphere are greenhouse gases. We know that water vapor, carbon dioxide, and methane are greenhouse gases, but we now want to see what happens if we have a lot of greenhouse gases or just a little bit, or maybe even none. So we're going to start our simulation. So we're going to press start sunlight. Oh, down the volume here a little bit. And so we can see the visible light coming in from the top here, from the sun. And as it's going towards the Earth here, towards the geosphere, it's being absorbed by the Earth, and then it's being re-radiated or emitted as infrared. And so that's shown in waves right now. So right now we have a moderate amount of greenhouse gases. Now that's probably pretty necessary, because if we change the temperature over here, I always have students change it to Fahrenheit because I don't think I have any students that really like understand Celsius temperature. So when we change it to Fahrenheit over here, what we see is that that creates a global temperature of about 40 degrees, right? So living things, they don't usually like very extreme temperatures. They like usually, for the most part, moderate temperatures. So 40 degrees seems pretty moderate. And so now what I want you guys to do is I want you to play with the toggle that's on the right-hand side, and I want you to explore what happens now when we either increase the amount of greenhouse gases in the atmosphere, or if we decrease them all the way to none. So I'm going to pause for a minute and let you guys do that.
And I went ahead and dropped that link in the chat so that if you didn't have to get the slides open or to have the sheet open, you still should be able to get into that simulation.
Maybe if you guys can just use your emotions, I think they're called. Is that what they're called? Emotions, captions, gestures. If you can just use your thumbs up gesture when you're done adjusting the greenhouse gases and looking at the temperature change, that would be great. They're even animated now.
They are.
Okay, yeah, great. I'm a little rusty on Zoom. It's been a while since I've used it a lot. Thankfully, I'm glad to be back in the classroom in person. Okay, so when we adjusted the greenhouse gases, hopefully we saw a relationship that when we increase the amount of greenhouse gases, that global temperature goes up, and when we decrease the amount of gases, that causes global temperature to go down. So what we're going to do now is we're going to build a model of our greenhouse gases. So in our document right here, this is a Google drawing. So we can double click on this and open this up. And what we're going to do is that now that my simulation is paused, I'm going to take a screenshot of my simulation here, screen. So I'm on a Mac, so that's Control-Shift-4 for me, but I think on a Chromebook, it's Control-Shift window switching button at the top. Now I've got my screenshot, and now I'm going to just drag it into my Google drawing. So it kind of appeared on the right-hand side over there, and then I dragged it in. If you didn't catch it quick enough, you can always go to this icon that's right here where it says image, and you can insert the image. Now, as I make my model bigger, you can see that my labels are all disappearing. So in order to prevent that from happening, I'm going to press down with 2 fingers on top of the picture on the trackpad. And that will open up this menu that allows me to change the order of the picture. And so right now the picture is at the front, and so I'm gonna send it to the back. Okay, and now what's showing is I can see all my molecules again. So I've got my carbon dioxide, I've got my methane, nitrogen, oxygen, and then I've got some of my labels down here: geosphere, hydrosphere, atmosphere. So what I want to do is just give you a minute to go ahead and move some of the components of the model here into their correct location. Again, try to think about what would a student do and try to replicate that. And then I also want you to add 2 labels by adding a text box, one for visible light and one for infrared. So I'll pause for a moment, let you guys do that, and then we'll come back together and adjust our model. Okay, again, just give me a thumbs up when you're ready to move on. Okay, so I will tell you that in my classes, what we got to really quickly is that we knew the geosphere was supposed to stay where it was supposed to go. And then the hydrosphere, students moved, oops, I moved the picture. Students moved the hydrosphere to the cloud, which I think made the most sense because that's where the most concentrated water vapor was. And then they moved the atmosphere to somewhere above the earth. And then we were kind of starting to get stuck. So students needed some help, needed some prompting, thinking about these gases up here. Okay, which ones were greenhouse gases versus which ones were not? So I definitely had to have students look back at the graph that they made in part 1 to think about which ones of these were greenhouse gases and had the ability to absorb heat and which ones did not. And so after we did that, then students kind of knew, oh, okay, carbon dioxide and methane, those are the ones that can trap heat in the earth. So, where do we see the heat being trapped? Well, we see the infrared is trying to escape here, and then it's hitting something there that's causing or pushing it back down towards the earth. So then students, would start dragging their carbon dioxide and their methane there. And then I said, well, what about, nitrogen and oxygen? And they're like, oh, well, they don't absorb infrared. And so students kind of landed on the idea that maybe it was best to kind of put those in between the waves of both visible light and infrared. So when we came back together, I kind of added a little bit of a layer of how prevalent are these gases in the atmosphere. Well, nitrogen is very prevalent. So I'm going to duplicate nitrogen and I'm going to put it in my atmosphere a bunch of times because it's the most prevalent gas, although it doesn't really interact with our infrared. But, we want our model to try and be accurate and reflective of the real atmosphere. So we're going to move some of these nitrogens around a little bit. And then oxygen is the next most prevalent. So let's duplicate that a couple times and let's move those around too, so that they're in between our waves. And so now out of methane and carbon dioxide, methane is in parts per billion. That's how it's measured. So that means, if we pull 1 billion molecules out of the atmosphere, maybe 1,000 might be methane. But carbon dioxide is measured in parts per million. So that means if we pull 1 million molecules out and we have 300 or 400 molecules of carbon dioxide, then the carbon dioxide is going to be more concentrated because it's out of 1 million molecules instead of out of 1 billion. So we are going to duplicate and at least add one more carbon dioxide molecule to our model because we only have infrared being reflected in this model in a couple of different spots. And that's kind of how we came back to our model, made some additional adjustments and layers to it, and then we saved and closed our model. And then students can use this model later on when they're working on the project to explain how the greenhouse effect works, right? So it kind of serves two purposes, helps them understand and build a model of what's happening to the Earth's atmosphere as the concentrations of the greenhouse gases are increasing, how they're working to trap the heat in, but then it also is going to help them on their project as well when they're working on that later on in the unit. All right, so at that point, students are going to answer a couple of questions. So earlier, you guys experimented with turning the temperature way up, turning the concentration of the gases way up and then turning them way down. And so we saw that the temperature dropped really low or the temperature got really hot. And again, living things don't usually do well in those extreme temperature environments. So life on this planet at least exists in part of having moderate greenhouse gases, right? So not having any, having too many, not really good for all the things living on the planet. And so now what we want students to do after they've answered this question is we want them to go back to the PhET, and we want them to explore what's happening with the water vapor in the atmosphere, because water vapor actually can play two roles in the atmosphere. So I'm going to start the simulation again, and I'm just going to show this to you guys so that we can do this observation together. But as we're looking at the cloud here and we're looking at the visible light coming into the cloud, we notice that some of it passes through, but then the cloud is actually reflecting some of that visible light back out into space. And so that's having a cooling effect on the Earth. If we get rid of the cloud, take that away, we can see that that visible light band has now gotten much thicker. So there's more visible light reaching the surface of the Earth. So the rocks are absorbing more of that. And then they're turning that into more infrared. So we have more infrared being radiated back up into the atmosphere. And we definitely see that we have an increase in temperature of about 7 degrees compared to when we did not have the cloud. So again, water vapor, they found out earlier in part 1 that water vapor can absorb energy, right? But it also can act to help cool the Earth as well when it's in ice or when it's in clouds, right? It can reflect visible light as well and prevent visible light from turning into infrared. So it kind of plays two roles, and you'll see that play out at the end of the assignment when students take two sides of an argument. So I'll pause that again. And let's go back to the simulation. So the last part of using the simulation is that, okay, now we know what the greenhouse gases are, and we built a model, and we've looked qualitatively at what happens if we have a lot of greenhouse gases or a little, but now we want to take some quantitative data. So we're going to look at different points in time, and we're going to check to see what were the carbon dioxide and methane concentrations at those times, and how did that impact global temperature. So for that, we're going to have to actually go over to a different tab on the PhET. So down at the bottom, there's 3 windows. We're going to click on the middle window, which is the photon window. And so now, instead of showing up as waves, the visible light and the infrared are going to show up as photons, just like they did in that first PhET that we looked at. And we're also going to click on the calendar icon on the right-hand side. That's going to make our time periods pop open. So right underneath the calendar is where we're going to find the concentration of gases. So again, in parts per million for carbon dioxide, in parts per billion for methane. And so, oops, there's a little typo in the template there. I better fix that. So this should be parts per billion. So we're going to collect what the concentration is there. We're going to press start sunlight. We're going to let it run until the temperature stabilizes, and then we will capture the temperature as well. So we're going to send you guys back into your breakout rooms. And again, if just one person can run the simulation at each time period, then we can collect that data quickly.
All right, I'm opening the breakout rooms now. And I'll go ahead and pause the recording while we're in there.
Is me correct? I believe the carbon dioxide concentration at the ice age should be around 200 parts per million. And I feel like methane was probably around 400, and that resulted in a temperature around 44 degrees Fahrenheit. And then when we move all the way to 2020 to present time, the carbon dioxide concentration doubles. So I feel like it's around 400 or something. The methane concentration goes up by 4.5 times. So I think it goes up to like 1800 and something. And then the temperature, I believe, rises to 55, 56 degrees Fahrenheit, somewhere around there. So that's really the big thing that we want students to see here, is that as we move through time, the concentrations of the gases, the greenhouse gases here, are increasing over time. That is causing the global temperature to go up. I did notice with students as they were writing their pattern, what pattern did you notice? Some of them were flipping the variables. So some of them were saying, well, the temperature is increasing and that's causing the concentration of the gases to go up. So just kind of an FYI to be on the lookout for that. Also, students need to do some observing about what's happening with the photons. And that's just, again, revisiting the idea that the visible light is coming from the sun. It's being absorbed by the earth, being re-radiated back into the atmosphere. And then again, kind of looking at the cloud and kind of that the infrared photons will get reflected back towards the earth from the cloud, but that the visible light photons, most of those will bounce off the top of the cloud. So again, the idea that water kind of has this dual effect. And it's part of what leads them to the final part of the assignment, which is where they are going to propose an argument for either side. So like, how could you be a scientist that would argue that more water vapor in the air would cause warming? How could you be a scientist that would propose an argument that more water vapor in the air could cause cooling of the planet, right? Because we definitely see this two-sidedness of water and its ability to both cool and heat the earth at the same time. So students use the sentence frames there, and then they finish out that assignment. And so then the next part of this assignment is the greenhouse gas concentration analysis. And that's where they really look at what's happened to the amount of carbon dioxide and methane over a long period of time, so over 800,000 years, and what are the sources of where those gases are coming from. And so it took us 2 full 90-minute class periods to do both parts of this lesson. And so we just finished the concentration portion today. So we can finish up or close out the slides and all of those things now and return to our professional development slide deck. And so again, what are the takeaways from this lesson? We definitely want students to know that carbon dioxide, methane, and water are greenhouse gases and that they do trap heat in, and that's what's causing the temperature of the planet to go up. These latter two would come from the secondary assignment. So carbon dioxide and methane concentrations have increased significantly in recent times. So when you look at the long-term graph, it kind of cycles up and down naturally for about 800,000 years. And then when it reaches 0 to 2000, then it is like exponential in its increase. And so that is very apparent. All students saw that very quickly, that was similar about both graphs, and that this is due, these concentrations, to burning of fossil fuels and agriculture. And then kind of a secondary one is just if you want to touch on the fact that carbon dioxide stays in the atmosphere for a longer period of time, but then methane is more capable or, better at trapping infrared into the environment. But carbon dioxide is more prevalent in the composition of the atmosphere than methane. So those are the key takeaways.
Right. So as we move on, we're not going to go as far in depth in the next couple of activities because both they haven't changed significantly since from the previous years, and we kind of went into them a little bit more in depth in the summer course. So after they've come out of their investigation of the greenhouse gases, they should have this sense that the temperature has gone up. And so we're looking at how the temperature impacts the particles and material. And so we sort of start off with this graphic of having them look at this and what do they notice and what do they wonder when they're thinking about the fact that the sea level rise in San Francisco, which is on the West Coast, is not as big as the sea level rise on the East Coast. So we start off with having them come up with questions for why that would be the case. And usually there's a big combination of someone often will bring up that it's warmer on the East Coast than the West Coast, but there'll also be we're closer to a glacier, there's bigger cliffs, there's a lot of reasons that go there. But what we do notice with both is that the sea levels are rising. And so we go through and we do an activity where we look at simulating what is happening with those particles. So there's a marble activity, there's a PhET simulation where they go through, can you go back, please? there's a marble activity, there's a PET simulation, and they look at how those particles are changing with time. And then they relate that back to, once they've done those activities, into trying to understand what causes the sea level rise. During the process of this, they're developing and using different models about what's going on with the particles, and practicing making those models and looking at how the energy is impacting the matter to make it change, and thinking about their definitions of energy. Go ahead and change slides now. The goal of this is to really get them to predict like why they think it's going, activate the prior knowledge, and then use this to review. Model how this is happening to the water as they watch the demonstration, and revise their model and explanation for the kinetic molecular theory. For some reason, when you switch slides, I thought we were on a different slide. All right. And the goals that we're trying to get from this set of activities, go ahead and go now, is that we can't just say that sea level rise can be accounted for by melting ice alone. I know that happens a lot in the media, but it's not the only thing that's causing the sea levels to rise. We want them to realize that thermal expansion of the water molecules is the big driver of sea level rise. And that's going to get worse as the temperature rises as well. And that the temperature of water on the East Coast is warmer than the West Coast, and so we don't see it or experience it equally as a result. Let's go ahead and go to the next slide. After that's done, and they've got to that the sea level rise is higher and it's due to those warming waters and the expansion, we want to see what the impact is on weather. So we look at what makes it rainy and dry. We look at the seasonal weather patterns. We start analyzing and interpreting data associated with temperature and how temperature impacts pressure and how pressure impacts weather. So we're looking at these patterns, and we're looking at how the weather and the climate go together. So the things that they learn in this is they start by looking at how to learn to read a weather map, which talks about pressure and warm fronts and cold fronts, so that they can think about different ways to measure temperature and pressure. Then they make a wild guess about the weather phenomena of what would happen if the temperature suddenly changed, which many of them have experienced, the temperature just going suddenly from 90 to 50 in an afternoon. At least my students have. And then you collect data from simulations or a wet lab, graph this in Desmos, and take observations. Now on the unit planner, we often recommend that people go with a simulation because the data is clearer and easy to see. I know that Jomae's had some really good luck with doing the simulation first and then doing the wet lab data afterwards, so that you can then compare the two and talk about what went going on with the wet lab that maybe cause the data to be similar or to be different. The wet lab
students did the wet lab, and they had an opportunity to design different procedures. So then by already knowing what the relationship was or what the pattern was already, it helped them to evaluate how well their procedure worked to collect the appropriate data.
Yeah. If you're planning on thinking of doing the wet lab, I do recommend that you test it out first. If you use too small of a container, or the seal doesn't fully set in there, the seal will pop and you won't really get the data that you're looking at. You have to heat those up very, very slowly to get the wet lab data to work, which is why oftentimes people will move back to the simulation to understand what's going on. They do work well together because the simulation does help you get a sense of what is actually happening in the wet lab if you plan on doing both. After they've done that, either one or the other, they do engage in a conversation about what does that all mean. And the key takeaways are to make sure that the pressure is directly proportional to temperatures. So they're just getting that Gay-Lussac's law. That those 2 points in a curve can be set equal to each other, and use that to derive the law. When particles stop moving at absolute zero, they don't collide with the container, resulting in a zero intercept. The other way that oftentimes we'll talk about it as well, if that seems a little off for folks, is to just say, is anything still a gas when we get down that cold? That our graph at some point also stops really making sense when we get close to that bottom temperature. And that the low pressure zones are associated with precipitation because the particles are moving more slowly. They move together, and that makes them stick together and drop down out of the atmosphere. They can't stay there. The particles rush towards these areas, rising in the atmosphere, cooling down, becoming more attracted to each other, and falling down as precipitation. I'm sorry, I said that a little strangely. Okay. Those high pressure zones are usually associated with clear skies because the particles are moving from low to high pressure areas and descending towards the surface and warming up. This is a great graphic to kind of help you see what's going on, of what's going with the high and the low pressure, so you can see what's causing the precipitation, what's causing those clouds to form and then form more rain.
All right, so that brings us into task set 5, which is where students are working on the climate change project. And so again, this is a great chance for them to go back to some of those questions that maybe they asked at the beginning of the unit that maybe weren't answered in the other 3 task sets. But how is climate change causing our weather patterns to differ in a location of your choice? So again, they want to pick a location that they care about. That could be a location that they want to visit or live someday. It can be a place that they have family or friends living. I generally tell students, because the example is on Portland, that it has to be, you know, outside of the Portland area. They have to pick a different place besides Portland. And we are an IB school, so we always like to bring in that global lens of looking at other places in the earth, but it does have to be someplace that is incurring some negative impacts due to climate change. And so this is probably the hardest thing for students in this project, is because most places of the world are experiencing multiple negative impacts due to climate change. And we really ask them to focus on one problem, because the scope of the project is really just not large enough for them to be able to address multiple problems. So I think narrowing the scope is sometimes what's most challenging for them. So the phenomenon is that the impacts of climate change are increasing, and they're becoming worse because the increase in global temperature is, you know, exacerbating. So in this particular project, they're working on the skills of obtaining, evaluating, and communicating information, and then also analyzing and interpreting data, because they are pulling in a lot of data sets to back up the claims that they are making in these particular projects. That are related, you know, maybe if they want to look at wildfires, or they want to look at sea level rise in their particular location, drought, you know, that kind of thing that's affecting agriculture. A lot of students have done that in the past. So, and then stability and change is really the cross-cutting concept here. So we've gone through periods where we can see, looking back at the graphs of carbon dioxide and methane, that there's always a natural cycling of global temperature with the greenhouse gases, but certainly the changes that we're seeing now are unprecedented, and we haven't seen changes like this before. And then our disciplinary core idea is climate change. So I made an example project for students so that they would know what we're expecting them to do. So after they choose their area, they want to explain the science behind climate change. So again, going back to that greenhouse model that we built earlier, hopefully they can use that greenhouse model to help them explain why the temperature is going up using their climate or their greenhouse model. They want to give evidence for their problem. Again, lots of different things that they can choose: hurricanes, tornadoes, sea level rise, flooding, drought, forest fires. So lots of choices here. And they want to determine the causes and the effects of the problem. So normally when we're focusing on a climate problem, we want to also say who it's affecting. That might be plants, it might be animals, it might be humans, it might be a specific culture. So they want to identify who is most negatively affected by that problem. And then we want to propose a solution and evaluate its impacts. So for the example project, a few years ago now, there was an article published in the Oregonian about redlining in Portland, and Portland State did a study in conjunction was somewhere in Virginia. I can't remember what institution now, but they studied historically red-lined neighborhoods and compared the temperature on the hottest days, so days that were 90 and above, with other parts of the city. And they found that Portland actually had the biggest temperature disparity. So for the problem in the example project here, it is related to that. So it says previously red-lined neighborhoods that include BIPOC, Black, Indigenous, and people of color are much warmer than white and wealthy areas due to the decades of discriminatory housing practices. This is causing a disparity in heat-related illnesses and deaths in BIPOC people. So we are very focused on equity at our school and bringing forth issues of social justice. So this was a great way to shine a light on a problem that is existing and that we are trying to move forward with, trying to find solutions to and enact solutions to reduce these disparities. So again, the first part of the project, we want students to articulate what's going on with temperature and the greenhouse effect. So again, hopefully they'd use their model here instead of this generic model and explain how the greenhouse effect is working. We certainly do have to have greenhouse gases in the atmosphere to make it hospitable on Earth to live, but too many is causing the temperature to rise too much. And then this is some specific information that is related directly to this problem. So this is a heat map of Portland that came out of that same study. And so it's showing the cooler areas of the city and the warmer areas of the city, and kind of showing why in some of these areas we have more heat because the surfaces that are used are mostly concrete or brick, whereas, we can look here, this is Forest Park, this is another forested or park areas. So in wider and wealthy areas, there were decades of time where trees were planted, parks were put in, and because of that now, that is resulting in this temperature disparity that we see in Portland in 2020. So that's explaining a little bit more about the cause of that specific problem. And then here is the graph that is showing the different temperature disparities from the different cities. So we can see that Portland's at the top here. And so it is the worst of all the cities that they studied. And they studied 108 different studies or cities when they did this study. So that is pretty, important that we have this big temperature disparity. And here's the effect that it's having on the biosphere, on people, right? So it is resulting in more people of color and also more older adults are dying because of heat-related illnesses and deaths. So we have some graphs here to explain that. And then this came out of an NPR study in 2021 where it is reporting heat-related deaths by zip code. And so we can definitely go back and look, the darker blue areas are where we're seeing more deaths, and those definitely overlap with our red-lined areas of the cities. And then now we want to turn towards what can we do about it? What are we doing about it? So this is multiple solutions that the city is considering. The city of Portland in implementing, I think they're planning on implementing all of them. But in the project, we ask students to kind of focus on one solution that they think is best and most immediate that area could implement. And so the easiest solution for the Portlanders is to start planting more trees, right? And so why planting trees will be important is because of the evapotranspiration that will help bring temperatures down. It will provide shade, right? So areas won't get so warm on those very hot days when it rises to 90 degrees and above. And so then down here we have some, people that are out planting the trees. And so there's a lot of other positive impacts to planting the trees as well. It saves the city money. The EPA found for every $1 invested in trees, it can save the city up to $3. It also provides habitat for animals. So again, positive impacts on the biosphere there. And it's an opportunity for the city of Portland to repair some of those damaged relationships that have been formed over these decades of discriminatory housing that has taken place for so long. So, and then we have, of course, our works cited at the bottom.
And I just want to add on to that a lot of times if you deal with climate issues like climate change, there is a small amount that you can get bogged down, and especially our BIPOC students can get bogged down into sort of like the despair piece of it. And the way through that and the way out of that is that piece, that's that focus on solutions. So even if all of the pieces that are related to the science are all about like what's going wrong and what's happened and the impacts, you need to make sure you still keep the part around like what kind of solutions are available, what community organizations are doing, so that you get back to the positive piece of what can we do about it, and don't just stay in the, well, why should I bother taking the rest of this class? We're all going to die, right? There's there's a little bit of that sort of in the world, and so it's really important to do that last piece around solutions.
Yeah, so that's how they're rounding out the unit in this particular case. And that brings us to one other new add to this unit, which if we go to slide 24, we created a series of rubrics for all of the task sets. So if you click on that link where it says Unit 1 rubrics, that should open you up to this spreadsheet. And so along the bottom of the spreadsheet, you should see each task set. So we've got task set 2, greenhouse gases. We didn't put task set 1 in there because that's where students are just doing the driving question board, and that's not normally something that's assessed. But what we tried to do that was a little bit different is that we tried to, for the criteria, list what the scientific and engineering practices were, the disciplinary core ideas, and the cross-cutting concepts, and then what that would look like at the different levels of proficiency. So I will have to say that some of these overlap. Like sometimes it was difficult to separate out, the practice from the disciplinary core idea and the cross-cutting concept. But this is draft 1, so this is the our best first go at it. And it hopefully will help all of you from having to write a lot of rubrics, at least giving you a point to start. And you can always pull it in and try it out and modify as necessary. I feel like we're always modifying and making our rubrics better at our site over time as we're utilizing them. So, but there's one for greenhouse gases. Sea level rise, we did split into part 1 and 2. So sea level rise part 1 is part of a density investigation. So if you do the full density investigation, then certainly all the components of the lab are here, right? We feel that students come in with a pretty solid understanding of density at our schools. So we kind of jump over that and we go right to the sea level rise part 2, which is the part of the investigation with the marbles and the thermal expansion and that portion. So we've got that rubric there as well. Gas laws, again, is an inquiry lab. So, we have many of the same things that you will see in the task set 3, the sea level rise part 1, because again, it's assessing students' ability to collect data, make a graph, analyze their data, and make conclusions. And then last, we have the climate change project. So when we were making the rubrics over the summer, we were really going back to the performance expectations. So the performance expectations that are linked to that task set are up in the top left-hand corner. And so what we noticed is that there are still some components that we need to add to the project in order to fully meet that performance expectation. And so those are the ones that you see highlighted right now. So we are in progress of working on that as we're working on the project right now during Unit 1, and you can expect to see those added in for the next version of the project that will be coming out next year. So that's why we highlighted those, just to indicate that the ones that are not highlighted are already currently part of the project. And then last, we pulled in the rubric from the example assessment that we looked at over the summer. And this time, since it is an assessment, it's very focused on the disciplinary core ideas. And so we just listed the 3 disciplinary core ideas down the side. And again, listed the different levels of proficiency here. All right, I think we've gotten to the end. Andrea, anything you want to say about the rubrics?
No, I think that was all great. I'm going to go ahead, and so at this point in time, we want to leave some time for questions. I'll go ahead and try to debate whether I should pause the recording for the questions or if I should leave it running so that people who might have the same questions can listen. I don't know. I'll leave it on for a little bit.
Right. You're so welcome for the rubrics.
I'll go ahead and stop the recording, and so that way people maybe feel a little bit more comfortable asking questions.